The distance of Mars orbiters from your location in U-direct Mars is given by s equal 2 times the quantity t minus 1 cubed minus 3 times the quantity t minus 1 squared plus 100 kilometers after t seconds, where t is non-negative, greater than or equal to 0. Obtain the extrema, points of inflection, and behavior at infinity. Sketch the curve and interpret these features in terms of the movement of the Mars orbiter. To answer a question regarding the extrema, we would need the first derivative. Points of inflection, we would need the second derivative. And the behavior at infinity, we will need to take the limit at x go to infinity. There's no need to take the limit at x go to negative infinity because t is 0 or positive only. First, we would need to find the first derivative s prime of t. S is a function of t. There's no need to multiply these out. We just simply use the power rule and the chain rule. The derivative of the first term is 2 times 3, which is 6, t minus 1, lower the power by 1, and then we multiply the derivative of the inside function t minus 1 with respect to t. The derivative of t minus 1 is 1. That is the derivative of the first term. Minus the derivative of the second term is 3 times 2, which is 6, t minus 1, lower the power by 1, and then multiply the derivative of the inside function. The derivative of t minus 1 is 1. And the third term, the derivative is 0. The derivative of a constant 100 is 0. Simplifying this, we have 6t minus 1 squared minus 6t minus 1. For the second derivative, we use the chain rule and the power rule as well. For the first term, the derivative is 6 times 2, which is 12, t minus 1, lower the power by 1, multiply the derivative of the inside, which is 1, minus 6, the derivative of t minus 1 is 1. And so the second derivative is 12 t minus 1 minus 6. We then take each derivative and set it equal to 0. Take the third derivative and set it equal to 0. This is 6t minus 1 squared minus 6t minus 1 equals 0. We will factor out 6 and t minus 1. What we have left is the factor of t minus 1 in the first term, and for the second term we factor out everything already, so we still have 1 left. This will give us 6 times t minus 1 times t minus 2 equals 0. This is a zero product. Using the zero product property, we have t equals 1. That is when the first factor equal to 0, t minus 1 equal to 0, t equals 1. When the second factor is 0, t minus 2 equals 0, t equals 2. For the second derivative, we set it equal to 0. This is 12t minus 12 minus 6 equals 0, or 12t minus 18 equals 0. This will give us 12t equals 18, or t equals 18 over 12. But we divide it by 6 to get 3 over 2. This is 1.5. The unit for t are all seconds. So these are seconds, second, t seconds. What do we do with these zeros? We will construct number lines for the first derivative. We only use the critical points or the stationary points that we found here. Those are the values of t that make the derivative equal to 0. And we found that it was 1 and 2. Then we test the sign of the first derivative. If we pick a number between 0 and 1, for example 0.5, and plug it into the first derivative, we will see that the first factor 0.5 minus 1 is negative, 0.5 minus 2 is negative, and a negative times a negative is positive. And so the first derivative is positive in the first interval. We then pick a number in the second interval from 1 to 2, such that 1.5, but any number will do, 1.2, 1.1, 1.9. So we'll pick 1.5, and we plug it into the first derivative to test the sign of the first derivative. If we plug in 1.5 into the first factor, we get 1.5 minus 1, which is positive, and then plug in 1.5 to the second factor. 1.5 minus 2 is negative, so 6 times a positive times a negative is negative, and so the first derivative is negative in the second interval from 1 to 2. And lastly, we pick any number in the last interval such as 100, but 3 will do. 3 minus 1 is positive, 3 minus 2 is positive. A positive times a positive is positive, so the first derivative is positive from 2 to infinity. We also do the same thing for the second derivative. For the second derivative as double prime, we will construct another number line right underneath the first derivative, but this time the number that we use is 1.5 or 3 over 2. If we pick any number from 0 to 3 over 2, such as t equals 1, and we plugged it into the second derivative, 12 times 1 minus 18 is negative. Lastly, we pick any number in the second interval such as 100, but 2 will do. 12 times 2 is 24 minus 18, that is positive. Armed with these two sign charts, we can answer questions regarding the extrema and the inflection point. We see that the function is increasing from 0 to 1 because the first derivative is positive, and then decreasing from 1 to 2 because the first derivative is negative in that interval, and then increasing from 2 to infinity. This means we will have a local maximum at t equals 1, and we also have a local minimum at t equals 2. The second derivative changes sign at 3 over 2 from negative to positive, the graph concave down and then concave up. Since it changes the concavity at 3 over 2, we have a point of inflection at t equals 1.5 or 3 over 2. Next, we will use the given function to obtain the distance. When t equals 1, s of 1 equals 2 times 1 minus 1 cubed minus 3 times 1 minus 1 squared plus 100. This is the given function s. 1 minus 1 is 0, we'll get 100. Next, we plugged in 2. When t equals 2, s of 2 is 2, 2 minus 1 cubed minus 3 times 2 minus 1 squared plus 100. This will give us 99. And when t equals 3 over 2, s of 1.5 equals 2 times 1.5 minus 1 cubed minus 3 times 1.5 minus 1 squared plus 100. And this will give us 99.5. The unit for s is in kilometers, so these are kilometers. We will use these information to sketch the graph of the function, sketch the curve. To sketch the curve, we will label any extrema, points of inflection. Also, we need to find the end behavior, the behavior at infinity. The function that we need to sketch is s of t equals 2t minus 1 cubed minus 3t minus 1 squared plus 100. The end behavior, or the behavior at infinity, is the limit as t go to infinity of this expression s of t. When t go to infinity, or t is a large number cubed is still a very large number. This is a polynomial, so the leading term determines the end behavior. What that means is that when t goes to infinity, a very large number cubed is still a very large number, or infinity. This is the graph that is drawn not to scale, meaning the x or the t-axis and the y-s-axis do not have the same scale. When t equals 0, 0 minus 1 cubed is -1, -1 cubed is times 2 is -2, 0 minus 1 squared is +1 times -3 is -3. So -2 minus 3 is -5 plus 100, which is 95. And so when t equals to 0, the y-intercept is 0, 95. We saw that when t equals 1, s is 100. And so we would plot 1, 100. The distance is 100 after 1 second. When t equals 2, the distance is 99, which is a little bit below 100. And also, when t is 1.5 or 3 over 2, the distance is 99.5. From 0 to 1, we see that the first derivative is positive, so the graph will be increasing, but the second derivative is negative, so it will be concave down. So we would need a curve or a segment that is increasing and concave down. From 1 to 1.5, the first derivative is negative, decreasing. The second derivative is negative, concave down. So from 1 to 1.5, we would need a segment that is decreasing and concave down. From 1.5 to 2, the first derivative is negative, so the graph will be decreasing, but the second derivative is positive, and so the graph will be concave up, decreasing but concave up. And then after 2, both the first and the second derivatives are positive, so the graph will be increasing and concave up, but also at t go to the right, then s go to infinity, very large. So increasing and concave up all the way. This is the graph of s. We see that initially when time is 0, the Mars orbiter is at 95 kilometers from us. After 1 second, it reaches its maximum distance at 100 kilometers, and then it will be coming closer to us as a decreasing rate or decelerating, and then it is accelerating, going faster and faster until it reaches its local minimum when t equal to 2 seconds after, at the distance of 99 kilometers. And then after 2 seconds, it keeps going further and further away from us.